All right, so Theorem 16. Let's do Theorem 16 here. That was a nice, lovely straight line there. Theorem 16 is literally the converse of Theorem 15 that we went over in the last video. And this is stating that if two straight lines drawn from a point in a perpendicular to a given line are equal, then they cut off equal segments from the foot of the perpendicular. So in Theorem 15, we said if these two straight lines cut off equal segments, then these two lines are equal. This theorem is stating if these two lines are equal, then they cut off equal segments. And so it's the same idea, but opposite. And many times in geometry, converses are true, but many times also they're not always true. And so we've got to be careful. That's why we have to prove the converse of that Theorem 15, because it isn't just automatically assumed to be true. And so here we go. Again, we're trying to prove that if those two lines are equal, they cut off equal segments from the foot of the perpendicular. I've already written down the first statement and reason. I haven't finished out the first statement, but let's finish it out real quick. We can say that RF is perpendicular to AB. Let's make that a little better. There we go. RF is perpendicular to AB. All I did there was write down the given information, and I get that given information from the theorem. They tell us that the two straight lines are equal, and they tell us that we have perpendicular lines. And so that's where I get the given from. We're trying to prove that DF is equal to EF. So this line segment DF is equal to EF. And so it's a very simple proof. It shouldn't take too long. So here we go. Let's talk about it. Number 2, we can state that angle 1 is and angle 2, they're both right angles. We can say angle 1 equals a right angle, and angle 2 equals a right angle. And it's the same reason as from the last video, because of the definition of perpendicular lines. All right, pretty simple. Number 3. We can say now that triangle PDF equals a right triangle, and a triangle PEF is a right triangle. Many times you don't necessarily have to say equal. You can say is a right triangle. I try to just keep it as simple as possible with the least amount of writing. Not a big difference, but you can say that. There we go. And the reason that they are both right triangles is because they both contain a right angle. So, definition of right triangles. There we go. Again, the next step, another simple step. We even saw this in Theorem 15. We can say, not PF, but let's make it RF. No, let's make it PF. PF equals PF, and that is because of identity. Again, let's just make sure we're not losing anyone. PF is the same line and is a side in both of these smaller triangles. There we go. Same line equal to itself. And so we can say that PF equals PF. Perfect. So we're pretty much already there. We can now prove that both of these triangles are congruent to each other by hypotenuse leg. We've learned that theorem a little bit ago. Hypotenuse leg, we've got two right triangles with one leg equal to another leg in a different triangle, and both hypotenuses are equal to each other. And so we can now say that these two triangles, triangle PDF, is congruent to triangle PEF. And then now we can say that the two line segments that we're trying to prove equal are equal by CPCTE. Okay, so corollary 16 is the converse of corollary 15.1. I'm sorry, corollary 16.1 is the converse of corollary 15.1. Very similar. And so let's just really dive quickly into it. We're not going to do a direct formal proof. We're going to do more of an indirect proof. we're trying to prove DF is greater than EF. So if two straight lines from a point in a perpendicular are unequal, if this is unequal or not equal to that, then they cut off unequal segments down here, and whichever greater line segment, straight line that we draw from the point in the perpendicular, whichever one is greater will cut off a greater segment from the foot of the perpendicular. So in this one, I just chose this side to be greater than that. You can choose either side, but I chose this one to be greater than that one, and I'm trying to prove that this line segment from the foot of the perpendicular is greater than this line segment, that DF is greater than EF, because I chose and put in the given that PD is greater than PE. Again, we have perpendicular lines. RF is perpendicular to AB. So to prove that this has to be true, that this line segment that is being cut off by a greater line segment is greater than this smaller segment being cut off by the smaller segment, I'm going to do the indirect way. So I'm going to lay this one aside and try to prove all the other possibilities to be true. If there ever comes a contradiction, then that must mean that possibility is not a correct possibility. And so obviously we have that DF is greater than EF. That's what we're trying to prove. But let's lay that aside and try to prove the other two possibilities. It's either equal to EF or it's smaller than EF. All right? So let's try to prove that DF is equal to EF. Well, we've already discussed and we've already had theorems, theorem 15 to be specific. If you hear banging, that's my daughter banging on the door. Gotta love it. I love it. So we have DF equaling EF, but theorem 15 says if a point in a perpendicular has two straight lines coming from it, and they cut off equal segments from the foot, then these two straight lines are equal. So if DF equals EF, that by theorem 15 would state that PD equals PE. Well, that contradicts what we're given in the given. The given states that PD is greater than PE. But if this were true, PD would equal PE. And so that means this is not a possibility, a valid possibility. Okay, let's look at if DF was less than EF. If DF is less than EF, again, corollary 15.1 said that if these are unequal, whichever side is bigger, it's being cut off by a greater line segment. So now we're working backwards. If this is smaller than this, that means this has to be smaller than that. So let's write that down. If this is true, then we would have that PD is smaller than or less than PE. Again, we find another contradiction. PD is already bigger or greater than PE. So if there's a contradiction, that means it cannot be true. And that leaves us with the only other possibility to be true. And so with the indirect method, we can prove that this is the only possibility to be true with this given, and really corollary 16.1 is just proven by that indirect method.